All right, this is the follow-up lecture from SSMs. It's on Mamba and Mamba 2. Um, so this lecture, if you didn't see the previous lecture, I strongly recommend watching the recording of the previous lecture before this. And so let's get started. So a quick review from SSMs. Basically, we have our two main equations. HT, which is your state, is equal to your A matrix, which is the thing that changes the state over time. And then plus your B matrix times your input. And then you have your YT, which is your C matrix times the state plus the D matrix times your input. Your D matrix is essentially your skip connection that takes the input to the output. Your C matrix transforms your current state into an output, YT. And your B matrix takes your input and shows how it affects the current state. And delta is the step size, which is also a learned parameter. So larger delta means more focus on a specific token, and smaller deltas means less focus on a specific token. So now we're going to be looking at Mamba from the perspective of a transformer, meaning we're going to be doing a lot of comparisons between Mamba and a transformer throughout this lecture. So the first thing is effectiveness versus efficiency. So in RNNs, they're extremely efficient. This is also from the previous lecture. They're extremely efficient in the sense that they just take their current hidden state to get their output, whereas transformers, they basically hold every single previous thing that it learned in training and then does a dot product with attention, which is really effective in getting the actual answer that you want, but it's not very efficient. And Mamba, what it tries to do is it tries to find the middle ground between these two things and improve on them. So basically it tries to get a really efficient model. It tries to be really efficient as a model while also having good effectiveness. So right now, from S5 in our previous lecture, there was no context dependence. So basically, once you have your parameters A, B, C, and D, they're set in stone like that, and they don't really change based on your input. So the main difference between S5 from before and Mamba is that now A, B, C, and D are parameters that change based on input or change based on time. So a quick review of S6 is that essentially you have your UT, which is now your input parameter, added to every single learned parameter A, B, C, and D. So now basically each parameter changes dynamically based on your input, and this is called selectivity. So because we now have selectivity, we're now able to improve on our effectiveness compared to traditional SSMs. And because our state size is bounded, we have a solid efficiency compared to your transformer. So what this means is now we basically have in context learning in a sense. So transformers only really decide what's important at recall time. So on short sequences, technically speaking, it's actually better to have a transformer. But if you remember from before, our previous lecture, Mamba was created for the sole purpose of dealing with long sequences. So Mamba lets the model have. So Mamba basically focuses on what to choose and what to discard. And it doesn't do this with attention, but instead does this with selectivity, where you're now throwing away less relevant information, and you're basically getting a compressed state for each parameter A, B, C, and D. So that makes it really good for long-range sequences compared to transformers of similar sizes. So essentially what's happening here is that you're now having your input parameters, your input parameter U is kind of being added to every single parameter B, C, D, and your step size and whatnot. And this allows you to have an input varying model. So the problem with selectivity, so if you remember from our previous lecture, we originally had this idea of basically taking an RNN focused like an RNN focused SSM and kind of like turning it into like a CNN in the sense that you can write it as a one-dimensional convolution and compute from there. So like you could take like your parameters like A, B, C, and D, and as your hidden state changes over time from like x0 to x2 and whatnot, your mod like you can kind of write this as a one-dimensional convolution to find yk. While originally you could kind of do this where like you're just like multiplying and like going like as from x0 to like xk all the way, and you're just like turning this into a massive multiplication with a as your recurrent parameter. What you can do is like do a one-dimensional convolution on this where you take like the stuff in green and you slide it one by one. So like on the first step, like your CB would be multiplying by U0 to get your Y0. On the second time step, you slide the green part over to multiply like CB times U1 and then CAB times U0 to get Y1. And you keep sliding one by one as a one-dimensional convolution to get your YK. And this was pretty fast because GPUs are fairly quick at like dealing with one-dimensional convolutions. The problem with selectivity is you lose this convolutional form. So instead, we use the hardware tricks from S5, and we sort of get this like a solid like runtime compared to before anyways, because we have parallel scans. And parallel scans are basically a scan from before. It's essentially just like you take your sequence elements, like for example, A1 to AL, and then a scan operation basically returns that multiplied by its factorial if it was multiplication. If it was division, it obviously wouldn't be a factorial, it would be repeated division. But you kind of have this like list of like factorials, and this is useful for SSMs because it allows you to very quickly compute your A parameter, which was a big deal, which was actually a fairly big problem back in like S5. So now that you can easily compute like your A parameter um with this parallel scan idea, it also lets you do like time varying, or also in other words input varying. It allows you to like have input varying parameters for your sequences, your input sequences specifically. So basically, you can now like have like a parallel scan where like normally you would kind of like compute this sequentially, right? You would just like multiply like each you would just kind of multiply A1 and then like A1 times A2, A1 times A2 times A3. The point is like you can like parallelize this pretty quickly. And that's why it's kind of called a parallel scan. This like fix was made. This is going to be used instead of the convolution, like the one-dimensional convolution. And so this was from like another article I saw earlier that I thought was fairly funny. Basically, like traditional RNNs are like they have a small minimal state, and like your size of the state is bounded. And transformers instead are like they have a maximally large state where they have like a cache of your entire history that's just compressed. Sorry, without compression. And then Mamba essentially has like a small state which is like compressed in a sense, and it's selective about what goes into the state. So now you have like small states which are like well focused and effective. So basically your A, B, C, and D parameters are like small like compressed states that hold like representations of everything. Transformers kind of do the same thing, except they're not compressed at all. They just kind of hold everything. So yeah. So from here, we have two big questions. Uh, what are the conceptual connections between state space models and attention, and can we combine them? So basically, SSMs are kind of fundamental in the sense that like they take like RNN, they take concepts from RNNs, CNNs, and sort of like put them together, and they kind of wrap it up into like one nice simple model, but they kind of feel disjoint from attention right now. So what Mamba 2 does in the next couple slides is it kind of like brings in attention. So the second question is like, can we speed up the training of Mamba models by recasting them as matrix multiplications? So right now, because while we do have parallel scans, they're fast, yeah, sure, but they're not as fast as matrix multiplications right now. Right now, modern GPUs are kind of highly specialized for like matrix multiplications, and uh, having parallel scans is like less effective than just like treating them as matrix multiplications. So what Mamba 2 does is it kind of like answers these two questions. So that introduces us to Mamba 2. So the main point of Mamba 2 is like your structured space duality is what they call it. The point of this is essentially like they kind of show a parallel between like attention and like SSM models, and then they kind of like prove that they're kind of the same equation. So like an SSD model basically refers to like a simple like layer. An SSM framework is like a general framework about like reasoning this model. And then the SSD algorithm is like the actual like algorithm. So like as these terms come up, just like sort of pay attention to them and just sort of remember them, or not, up to you. Um, so regarding like structured space dualities, what's different between these and SSMs might be your first question. So it essentially defines like a map. Originally, we had like a simple map, right? With our like, these are our two fundamental equations of SSMs, like your HT and YT. It's basically just a map from input X to output Y. And you have like a diagonal structure A with like your shape. A is essentially like your tensor or a matrix in a sense. And it's got the shape like T and N. And then your SSD basically restricts A further by having the diagonal elements as just scalars. So before, our diagonal elements uh were originally like learned parameters. Now we're keeping them as scalars. You might wonder, like, does this restriction make the model perform worse? It turns out it actually doesn't. And more information just goes into B and C, and the information that was originally in A gets transferred to like something we call an attention mask, which is coming up. So this is just like a basic like intro of like multi-head SSMs. We're going to be talking about like single head SSMs from this point onwards. But if you want to know like how it kind of looks as like a big picture, like a multi-head SSM just has like your parameter P, where P is like the dimension of your head. And the heads in Mamba 2 are basically exactly analogous to like multi-head in a transformer. And so like similar dimensions are kind of chosen between Mamba 2 and transformers to compare them. So like a Mamba 2 would have like a multi-head of like 64 or 128, and it would be compared to similar like multi-head attentions in like transformers. And so the general state space model for our multi-head attention is you just add the parameter t, and then you kind of have like basically the same equation. So y is like a function of x put into your SSM. So now we're going to be drawing parallels to attention from like our SSMs. So basically, we start by defining our matrix L, and we're going to define it as such, where basically it's a lower triangular matrix, while all of the diagonal elements are just one. And we define M as like your matrix L multiplied by our learned parameters C and B. And M basically encodes like your sequence transformation, which maps like X to Y, your 1D input to your 1D output. So now that we've defined L actually turns out to be our like important attention mask, which is going to be used later. So before we get to L and what it actually does, we're going to talk a little bit about like matrix mixers. So basically in many sequence models, you're kind of like transforming your input X to like some output Y. And this can be written as like a matrix multiplication, like Y equals mx times X, where M is like your matrix depending on X, which is your input. So this is called either a matrix transformation or a matrix mixer, depending on like what papers you're reading. They kind of use them interchangeably. And one example of a matrix transformation is self-attention, right? So like M in like a normal transformer would just be like your softmax of your query and key values, query and key matrices, sorry. And that's like your attention matrix. And then in like, and then RNNs and LSTMs can't actually be written as matrix mixers, but SSMs can. And SSMs are written as like Y equals like your SSM with your parameters A, B, and C multiplied by X. Or essentially you can rewrite SSM of A, B, and C as just M. So our M is basically like the exact same equation as like linear attention, uh, if you rename the parameters like from before. So what they do is they create this equation like M is like equal to like L, which was your quote unquote attention mask, multiplied by your learned parameters C and B. And it's essentially equal to something called casual linear attention, which is just as a side note, casual linear attention is different from like the attention that you learned in like the attention is all you need paper. Casual linear attention is like they just do some extra like kernel operations. And other than that, it's like kind of mostly the same. Um, and like this is kind of called state space duality in the sense that like it's like you can kind of view it as either like a matrix multiplication or you can view it as an SSM. So what people do in practice is they tend to train it sort of as like in this matrix multiplication way, and then they like use it in the SSM way. So you're kind of training it like sort of as a transformer in a sense, and then you're kind of using it in your like general RNN sense that we've been doing since last lecture. So yeah, L is essentially your a lower triangular casual mask, which is kind of similar. Yeah, what's up?
So is this like, if you're saying this like what you train it as, is this like replacing the like convolutional mode kind of?
Basically.
Yeah.
So now you can kind of view this as like a function where like you're taking your A, B, C, and X and you're turning it into your output Y. Yeah.
Take a second to send your slides.
Yeah. Let's send it.
Then this is in the Discord.
Yeah, sure. Like,
Are you good on time?
yeah, I'll finish early. This lecture is fairly short. All right. Yeah, like this is like heavily dependent on like the last lecture. So yeah. Basically your full matrix representation is kind of like you're taking your like M, like from this equation earlier, M is like your L, which was this, multiplied by your C and B to sort of get that. And this is your full matrix representation of a state space model. And you're kind of just taking your inputs, putting them into this lower triangular matrix and getting your outputs. So now Mamba 1 has like a diagonal A matrix where now we have Mamba 2 set as like our scalar times identity structure, which is basically just means like you have a diagonal matrix, but every single diagonal value is the exact same value. And Mamba 1 originally had like a head dimension of just like p equals 1, and then you would kind of put multiple of these dimensions together and then mix them together with an MLP layer to try and like understand how the layers interact with each other. Now we just have like multiple head dimensions and they kind of operate like that. So basically, we say that transformers are basically like a case of an SSM. Since you can write your SSM in like in this like matrix form, you can kind of say that transformers and attention are like a specific case of it. And that's kind of what their paper goes over, um, but with more math. So basically, when you're comparing it to attention, like the normal attention in like Vaswani's paper of like attention is all you need, uh softmax is obviously dropped. But instead they have like an element-wise mask matrix, or basically their quote unquote attention matrix, which was like the L that you saw earlier. And this mask is kind of like input dependent relative to your positional encodings. So what that means is like, so for the positional encoding part, it kind of modifies how the tokens from like previous, like from like the start of your sentence, uh, like it kind of modifies how those tokens interact with like future tokens. And it effectively encodes like your relative positional information with these like state transitions from H to like H1 to and so on. So basically, if you had to give an example, like in Transformers, these two sentences would have the exact same positional encoding. However, in Mamba 2, your L, like your mask, uh, is kind of different for each of these, and it adjusts how like your state updates, like it adjusts how state updates are propagating based on like the meaning of the words. So it like values both of those sentences differently in terms of positional encoding alone. And that's kind of what makes it more adaptable towards like different sentence structures. And it doesn't need like some kind of explicit global attention. So overall, it's like a little bit more memory efficient and a little bit faster than transformers right now. So like if you had to like process a sentence, for example, uh say your sentence of your input X is like the quick brown fox jumps over a lazy dog, right? Uh your tokenize you first tokenize your inputs sort of like just in a transformer. Once you get uh your tokenized inputs are put into embedding, like into embeddings, and each embedding has a certain dimensionality. In this case, we're going to assume that like our word embedding has like 512 dimensions. And if we had like our head dimension, like say our head, like say in Mamba 2, we had our head dimension of like p is greater than 1. Generally, it's like 64 or 128. So if like our multi-head like Mamba 2 had like 64 heads, that kind of means that like the 64 heads process all of your tokens at once, but they process like each like 64 dimensions out of those 512 dimensions. So next, we also update your hidden state with the SSM equation. So basically, if this was instead training, like for example, instead of actual like in context learning, if this was like in the training stage, it would update with like the matrix multiplications I described earlier. Like your hidden state is just like your L matrix times your input, and your final hidden state is transformed into your output like Y, which is like your C parameter multiplied by your hidden state. And that's kind of similar to the SSM from before. This leads to like the recurrent view from last lecture, and it kind of leads to like very quick like inference time. So like some general benchmarks of like Mamba 2 are that like in general it just like does quite a bit better than like some hybrid models and like some transformers. It's also like quite a bit faster in terms of like time when it comes to like both inference and training. And the only real important thing to note here is that like originally like SSMs and Mamba were made for the sole purpose of dealing with like long range dependencies. So in these long range dependencies, like it does actually perform quite a bit better compared to transformers of similar size. And later we kind of go over like hybrid models. So basically like, or we don't go over this actually, but like later like people like in general have just kind of been making hybrid models like on the side. Um because your Mamba 2 blocks are like extremely like they're extremely similar to like a normal like self-attention block. you can kind of like easily make hybrid models. So that's kind of what people have been doing. Like, for example, one is like Samba, as shown in the image here. They kind of like replace like your normal like attention heads with like 6 Mamba blocks or Mamba 2 blocks. And they kind of mix it in with like attention heads. And this actually ends up performing, hybrid models in general tend to perform a little bit better than like some well-known transformers. Like, for example, this one tends to perform better than like Llama 3 of like 8 billion parameters, since this one's also 8 billion parameters. Especially in terms of like long range dependencies, it actually does perform quite a bit better. So basically, Mamba is now encoding like information into these compressed hidden states, which allows it to like deal with like these long range dependencies quite a bit easier compared to, say, a transformer. So like some basic metrics on Zamba are like you have like solid like inference speed, solid like output generation speed, and you have quite a bit lower memory usage in general compared to like transformers. And the actual output is like and it's like this isn't shown here, but it also had like a perplexity score of like that was quite a bit lower. So in other words, as you can see, it's benchmarking against like Llama 3 of 8 billion parameters and like Mistral and Gamma. So yeah. Basically, in future research directions, what the authors have stated at like towards like the very end of their paper is that they kind of like acknowledge the existence of hybrid models, and they mentioned that hybrid models were like fairly efficient, or not efficient, but rather they sort of combined the effectiveness of a transformer with like with Mamba's ability to deal with long range dependencies, and they actually end up performing better than like normal transformers. So what a lot of people have been doing since then is they've kind of been making these hybrid models, and that's kind of the state we're at right now, or at least that's the state we were at until Google's Titan paper came out, and that completely crushed Mamba in basically every single benchmark. Anyways, that was essentially the end of my lecture. As I said, like a lot of this was covered in the previous lecture. So like, yeah, what's up?
So like, would you say that Mamba and like Mamba 2 and even like hybrid models are kind of like obsolete, or do you see any chance of it kind of like making it come back?
When it comes to like Google's new paper where they use like memory as a gate, memory as a layer, and all this other stuff, in terms of like training time and compute time, it's actually like a little bit like less efficient, because it's just like a lot more stuff. So like in terms of speed, it's like better. Of course, as improvements are made, I don't really know for sure, but like I can see them going like slightly more obsolete over time. But like there are existing hybrid models right now that are like not terrible when it comes to like next word generation, sort of like GPT, or like dealing with like other things, like for example, DNA sequencing and stuff like that. When it comes to things that are purely meant for like long range dependencies, like DNA sequencing, Mamba's doing pretty well right now. When it comes to like next token generation, when it comes to like modeling language, yeah, I can see them phasing out. So yeah, that was kind of the end of this lecture. Once again, it was like heavily dependent on the last lecture. So yeah. Thank you for listening.